Rational zeros theorem. Let f be a polynomial function of degree 1 or higher of the form fx equals a sub n x to the n all the way down to a naught. And an cannot be 0 or a naught cannot be 0. So this means we have to have a number here and a number here that's non-zero. So now it says where each coefficient is an integer, so a1 through an are all integers, and lowest terms. Integers. And then it says if p over q in lowest terms is a rational zero of f, so if this is a rational zero of f, then p must be a factor of a naught. So that means p goes into a naught evenly, and q must be a factor of an. So that means q goes into an evenly. So below here, we have a problem that it says, for the following exercises, list all possible rational zeros for the functions. So what we're going to do here is we're going to use this theorem here, the rational zeros theorem, to actually find all those possible zeros. And we're going to use the idea that we see here. P must be a factor of a naught, q must be a factor of an, and p over q is a rational zero of f. So we're going to use all that information to figure that out. So first things first here. So first I have to understand what p is. Now p is a factor of a naught. So that means for our problem here, it would be a factor of 4. And that's a positive 4 at that. So I'm going to think of plus or minus 1. And I'm going to write them out separately. So negative 1, positive 1. I was going to write the positive sign, but I don't have to. And then negative 2 and positive 2. And then positive and negative 4. So negative 4, positive 4. That's all the p's. And then the q's now I'm going to do next. So q's must be factors of a sub n. So our a sub n term is right here, and that's 1. Because when we don't see a number there, it's understood to be 1. So negative 1, positive 1. So now what I'm going to do is I'm just going to list them all, because this says if p over q in lowest terms is a rational zero of f. So now what I'm going to do is I'm going to list all the p over q's. So the first one is going to be negative 1 over negative 1, and then 1 over negative 1, and then negative 2 over negative 1, and then 2 over negative 1, and then negative 4 over negative 1, and then 4 over negative 1. So what I did first here was take all of the numbers of p and divided them all by negative 1. So now these all simplify, of course, but I'm just writing them all out. So now I'm going to do the same thing with 1. Negative 2 over 1, 2 over 1. Now just with the positive 1. Negative 4 over 1, and then 4 over 1. And what we see here is when I clean these lists up, or simplify them, I should say, I'm going to start with the top one here. And I'm just going to write those down below in simpler terms. So 1, negative 1, 2, negative 2, 4, negative 4. And I'm going to do the same thing with the bottom list now, just below that one. And that's going to be negative 1, 1, negative 2, 2, negative 4, 4. And you can see that both these lists are the same. They're just in a different order. So we don't need them all. And one thing we'll realize is when I have this plus and negative 1 on the bottom and I divide each of them by it, it's always going to create the same list because I'm using all the same numbers on the top here. So I don't have to write these out ever again twice this way. And that's what I wanted to point out to you. So I could just simply write negative 1, positive 1, negative 2, positive 2, negative 4, positive 4. Because if I go negative or positive, all that does is just change the order in which they appear in the list. So that would be sufficient for this. So this exercise was pretty nice. That's all of them. And then, like I said, the negative 1 divided by each of those, and then the positive 1 divided by each of those is going to result in the same list. And that would work also if I had different numbers, like a 7 on the bottom. The positive and negative would generate the same list if I have used the same numbers. So there's our answer. All we had to do was list those.